Everybody, and welcome to the only place where bedtime stories involve solar incineration and physics that wants you dead. Tonight, you drift silently through the cosmos, surrounded by stars, distant and twinkling, peaceful as they shimmer in the darkness. But one of them isn't playing by the rules. One of them is blazing at 200,000 degrees Celsius. That's over 35 times hotter than the sun's surface. It doesn't twinkle. It roars. It doesn't whisper. It screams light into every direction. You look at it, barely. Your eyelids slam shut as if they're doing you a personal favor. Even from thousands of light years away, your skin prickles. Your atoms start sweating. You probably won't survive this, but hey, what a way to go. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me, where are you listening from, and what time is it for you right now? Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift closer. From afar, it looks like a brilliant blue bead, calm, confident, almost inviting. But don't let that serene glow fool you. Blue stars are deceptive. They are the dragons of the stellar world, furious, young, massive, and entirely uninterested in being your friend. This one is even more extreme. A rogue overachiever in a galaxy full of hotshots. It's burning at 200,000 degrees Celsius, and that's not its core, that's just its surface. Deep inside, the temperatures spike to millions. The center isn't so much a place as it is a nuclear tantrum held together by gravity and regret. You start to imagine what that heat would feel like, not metaphorical heat, not summer in Saigon heat, but real, unfiltered stellar rage. The kind that strips electrons off atoms, pulverizes molecules into bare nuclei, and laughs in the face of anything remotely solid. This isn't just a hot star. It's what astrophysicists call a Wolf-Rayet star, the cosmic equivalent of a short-fused bodybuilder sprinting toward cardiac arrest. These stars form when the most massive stars in the universe shed their outer layers and expose their hot, violent cores. You can thank high mass and low chill for this hellish outcome. And you're floating right toward it. Here's the wild part, this star could actually be smaller than the sun in size, yet way hotter and brighter. Why? Because it's concentrated danger. Like the difference between a cozy campfire and an industrial blowtorch that vaporizes steel beams. You squint through the void, watching the star pulse ever so slightly, tiny ripples racing across its surface like boiling soup. Some of those waves are called stellar winds, but don't let the word wind confuse you. These are high-speed streams of particles shooting out at thousands of kilometers per second, capable of shredding planets, stripping atmospheres, and casually writing off entire solar systems. It's not just heat you're dealing with. It's pressure. Gravity. Magnetic chaos. The raw fury of fusion. If the sun is your gentle neighborhood furnace, this is the industrial incinerator of the universe. Back on Earth, the hottest thing you can touch is probably a bolt of lightning, around 30,000 degrees Celsius. Touch this star, and your atoms file for divorce. And yet, it's beautiful. That's the dangerous part. The blue hue is hypnotic. Your eyes don't register danger, they register allure. It's the same reason people are drawn to volcanic lava or the glittering glow of deep-sea creatures that really don't want to be touched. But if you're wondering why stars like this even exist, well, we don't totally know. That's part of the mystery. Historians still argue whether early civilizations even noticed stars this rare, or whether their brilliance was dismissed as gods throwing tantrums. There's a story, buried deep in ancient Mesopotamian tablets, of a star that appeared only once in the lives of 3 kings. Was it a comet? A supernova? Or a flare from a star like this one, so rare, so fleeting, it made the sky blink for a moment and vanish again? The truth is, we didn't even know about most of these monsters until we had space telescopes. The atmosphere is just too thick and noisy to spot them from Earth. But now, with infrared eyes in the void, we can finally peek at these hotheads as they scream their radiation into the dark. And what a scream it is! As you float closer than safety would ever permit, you feel time begin to stretch. Not metaphorically. Literally. The gravitational field here is strong enough to mess with time itself. Seconds tick by slower. Your heartbeat feels drawn out, as though the star is trying to pull you into its rhythm. Which, let's be clear, is not a safe rhythm. Stars like this have lifespans measured in millions of years, not billions. They burn fast, live hard, and die loud. And this one is halfway through its own cosmic roller coaster. But don't worry, we're not skipping ahead. We'll get to the explosive part later. For now, just float. Listen to the static roar. Watch that swirling dance of light and plasma. You're staring into a burning question mark, a star that shouldn't be this hot, yet somehow is. You wonder what kind of fuel it's burning. You'll find out. You wonder how long it's been burning. We'll get there too. And you wonder, maybe quietly, if Earth was ever this hot in its early days. Spoiler, no. But Earth does share atoms that were once born in stars like this one. That oxygen you just inhaled could have been forged in a stellar blast thousands of light years away, long before the dinosaurs even dreamed of existing. The universe has a weird way of connecting dots. And as the star flares just slightly in your direction, lighting up a gas cloud 10 light-years across like a bonfire catching a wedding veil, you realize something strange. It's not trying to kill you. It's just being itself. Unapologetically, spectacularly, catastrophically hot. You're drifting backward in time now, not by choice, but because the story demands it. To understand this blistering furnace of a star, you need to see how it became. Not just the fireball you met a few light minutes ago, but the colossal cosmic tantrum that gave birth to it. So you rewind, past flare-ups, past the fusion chaos, all the way back to where this monster first took shape. It starts in darkness. Deep, cold space. A vast cloud of gas and dust, silent and still for millions of years. You float through it, miles wide, soft as breath, and utterly forgettable at first glance. This, believe it or not, is where the most extreme stars in the universe are born. Then gravity happens. Not suddenly, not loudly. Just a quiet tug. A few hydrogen atoms get cozy. Then a few more. Tiny collapses, invisible over lifetimes, start to snowball. And eventually, after enough squeezing and swirling, you get heat. A lot of it. Somewhere inside that dusty cradle, a protostar forms, basically a glorified space fetus with delusions of grandeur. It's dense. Hot. Glowing. Angry. Kind of like a toddler, except it weighs a few dozen suns. Now, most stars stop here. They reach a nice balance, gas pressure pushes out, gravity pulls in, and everything's fine. They settle down, start fusing hydrogen into helium, and prepare for a boring billion-year middle age. But not this one. This one is born too big. It pulls in so much mass, so fast, that balance never happens. It doesn't simmer. It detonates into existence, like someone lit the fuse on a bomb and whispered, "Good luck," as they walked away. The star begins fusing not just hydrogen, but anything it can get its core around. Helium, carbon, even heavier elements if it gets cocky. It's a fusion buffet, and everything's on the menu. This phase is hot. Hotter than most stars ever get, even at their peak. And it's just a baby. The star's core starts behaving like a pressure cooker that someone forgot to turn off. Temperatures climb past 1,000,000 degrees. Then 10 million. Then more. You blink, and the outer layers are blasted outward, stellar tantrums that would shame any volcano on Earth. You watch as massive waves of radiation shoot out, lighting up nearby clouds of gas like neon graffiti on the walls of the galaxy. Astronomers call these regions HII regions, massive, glowing birthplaces of stars, painted by ultraviolet radiation from their hotter siblings. One of them. It's being lit up by the very star you're watching form. This, you realize, is the natal scream of a blue hypergiant. A cry so loud, it echoes across star systems. And if you're wondering how big this gas cloud had to be to birth a star like this, well, we're talking dozens of solar masses. Some scientists believe these stars can only form in starburst regions, like the cores of dense galaxies or chaotic clusters where stars are being born like popcorn in a hot pan. There's an ongoing debate among astrophysicists about just how massive a gas cloud needs to be to form a star this hot. Some argue it's about the cloud's metallicity, how many heavy elements it contains. Others point to turbulence, magnetic fields, or even collisions between other clouds. Historians still argue whether ancient astronomers ever spotted such a star being born, or whether myths about sky fires and cracking heavens were just colorful meteor showers. Some tales from early Polynesian voyagers describe the sky splitting open with blue flame, a poetic exaggeration, perhaps, or an actual celestial event lost to time. Either way, you're here now, watching as this insane accumulation of gas and fury becomes a 200,000 degrees Celsius monster. And even as the star stabilizes, it keeps shedding mass, violently, dramatically. It spins fast. Its poles flare. Its equator throws tantrums. And around it, the remnants of its own formation spin like a glowing necklace, gas, dust, maybe even early planets, if they're unlucky enough to form. You drift through that debris, a mix of everything from pure hydrogen to rare isotopes that don't even have proper names yet. This stuff isn't just space junk. It's the future. It'll get picked up, pulled in, maybe even become part of a new solar system one day. Or, not. Because let's be honest, anything near this star is basically toast. Back on Earth, scientists study these formation stages through infrared telescopes, peeking through dust clouds that would otherwise hide the action. One of the first detailed images of a hypergiant's birth was captured using the Spitzer Space Telescope, a picture that looked less like a nursery and more like an explosion at a glitter factory. And just for fun, some legends from the Dogon people of West Africa describe a star so hot, it made water boil in rivers at night. The accuracy of their astronomy has long sparked debate and controversy. But who's to say they weren't watching something spectacular? You hover at the edge of this newborn inferno, staring at what's essentially the worst place in the galaxy to set up a picnic. The light here doesn't twinkle, it pulses. The wind doesn't blow, it slices. The space isn't empty, it vibrates with fusion and flare. The star is fully formed now. It's no longer just a mass of gas. It's a machine. A generator. A cosmic pressure engine that runs on time, heat, and regret. It's alive in the only way a star can be, burning, aging, dying, all at once. And it's just getting started. You hover now, just beyond its deadly reach, watching it settle into something terrifyingly beautiful, a blue hypergiant, fully grown and endlessly burning. Not just hot. Not just massive. This is one of the rarest types of stars in the universe. A member of an exclusive club, the kind that doesn't hand out lifetime memberships because, frankly, these things don't live long enough. They shine like gods and die like firecrackers. This star, at 200,000 degrees Celsius, is already an overachiever. But it's not alone. Not entirely. There are others, rare, scattered across galaxies like cosmic exclamation marks. You drift sideways through space, crossing light years in seconds, visiting a few of its distant cousins. Say hello to Zeta Puppis, a blue supergiant visible from the southern hemisphere. Only 4.5 million years old. Already more than 20 times the Sun's mass. Its surface temperature. Around 40,000 degrees Celsius. Not quite the beast you're watching, but hot enough to sear your curiosity. Then there's our 136A1, tucked inside the Tarantula Nebula, a star so massive it barely makes sense. Scientists believe it began with over 300 solar masses. That's obscene. That's cosmic cheating. And it's burning at close to 50,000 degrees Celsius, still nowhere near your 200,000 degree companion, but a heavyweight nonetheless. These stars belong to the O-type and WR-type categories, the heavy lifters of the cosmos. They emit so much radiation, they literally carve tunnels through nearby gas clouds. If the Milky Way were a jungle, these stars would be the machete-wielding explorers, slashing paths through interstellar thickets. And you're tagging along with the hottest one of them all. The color blue here isn't accidental. It's a sign of heat. The hotter a star, the bluer its glow, just like a blowtorch flame. Our sun is yellow because it's warmish. This one? It's the deep, royal blue of danger. You look closely, your imaginary eyes shielded by layers of make-believe protection, and notice something curious. The star isn't smooth. It's writhing. The surface undulates, pulses, ripples with turbulence. It's like watching boiling syrup, if the syrup could kill you with X-rays. Inside, fusion rages. On the outside, it blasts out solar wind so strong, it rivals entire hurricanes in mass and velocity. These winds are made of ionized particles, mostly hydrogen nuclei, flying at millions of kilometers per hour. If the Earth were this star's neighbor, our entire atmosphere would be gone before you finished this sentence. There's a strange beauty in all this violence. That contradiction, fury and elegance at the same time. It's like watching ballet performed with chainsaws. You can't look away. Not many of these stars exist. Maybe only one in a few million is this hot. Some galaxies may not even have one at all. The conditions needed to birth a star like this are rare. It's like making a soufflé in a tornado, you need just the right mix of chaos and calm. Astronomers still debate whether binary systems, stars born with a companion, are more likely to evolve into blue hypergiants. Some theories suggest that intense mass exchange between sibling stars can strip away outer layers, exposing hotter cores. Others think it's mostly about initial mass and luck. And then there are the runaways, stars kicked out of their original homes by gravitational bullying. One such star, AE Aurigae, is believed to have been ejected from its birthplace and now races through space at over 100 kilometers per second. Not a hypergiant, but a reminder that even stars have drama. You pause, floating quietly near your 200,000 degrees Celsius star, and reflect on how short its life will be. A few million years, maybe. A blink in cosmic time. It's the fast-living rock star of the universe, flaring bright, burning out young, and leaving a stunning mess behind. And yet, in its brief existence, it shapes everything around it. The light from this star reaches distant nebulae, triggering new stars to form. Its radiation alters chemistry in nearby systems. Its eventual death will scatter heavy elements across space, ingredients for planets, oceans, and maybe even life. There's an ancient Chinese myth about a star so bright it turned night into silk. Some historians think it referred to a supernova, possibly even the death of a hot star like this one. But others argue it might have been a hypergiant spotted at just the right moment, flaring wildly. Either way, the impact of these rare stars reaches far beyond their neighborhoods. Right now, scientists are using instruments like Gaia, James Webb, and the Very Large Telescope to track them, scan them, decode them. But there's still so much we don't know. Why do some burn at 40,000 degrees Celsius, while others reach 200,000 degrees Celsius? Is it just mass? Age? A bizarre twist of stellar fate? Even the exact number of hypergiants in our galaxy is fuzzy. We think we know. But every time we build a better telescope, the math changes. Just like that time you thought Pluto was a planet, and then it wasn't. Space doesn't care about your flashcards. One thing's certain, blue hypergiants are rare not just because they're hard to make, but because they're hard to keep. They teeter constantly on the edge of stability. Gravity tries to hold them together. Radiation tries to rip them apart. Your star. It's currently winning both battles. But not for long. You're getting pulled deeper now, not physically, but into the very engine room of this star. You want to understand how it burns so violently, how it maintains that ludicrous 200,000 degrees Celsius surface temperature without melting into oblivion. Welcome to the core. Not that you'll actually get there. At least, not intact. But imagine, just for a moment, you could survive the journey, a fantasy bubble around you, like a protective dream. You descend through swirling plasma, diving below the blinding surface layer called the photosphere, into deeper layers where light takes thousands of years to escape. Inside, it's chaos, but structured chaos. Like a nightclub run by physicists and staffed entirely by atomic nuclei. At the center, temperatures soar into the hundreds of millions of degrees Celsius. Pressure builds to a level you can't imagine, greater than anything on Earth by a factor so big, it's basically a punchline. This is where nuclear fusion happens. But not the polite kind you learn about in school. No, this is fusion on steroids, atoms crushed together so hard that they transform. Hydrogen becomes helium. Then helium becomes carbon. Then carbon becomes even heavier stuff, oxygen, neon, silicon. Each step releases energy. Lots of energy. Enough to keep this monster puffed up against its own crushing weight. Without it, gravity would win, and the whole thing would collapse like a soufflé in an earthquake. You float just above the core, imaginary, safe, and watch as protons scream into each other at breakneck speeds. The collisions are frequent, furious, and precise. This is nature's most ancient and elegant power source. What's astonishing is how little material actually gets converted to energy. Just a tiny fraction of mass, E equals mc squared and all that, but the payoff is astronomical. Literally. That tiny bit of mass loss becomes the light and heat blazing from the star's surface. Still, not all stars fuse the same way. The Sun, for instance, uses the proton-proton chain reaction, a relatively slow and chill process. But here, inside your 200,000 degrees Celsius behemoth, a different method takes over, the CNO cycle. That stands for carbon, nitrogen, oxygen, a catalytic cycle where these elements help fuse hydrogen into helium. It's fast, violent, and incredibly efficient at higher temperatures. This is why your star can produce so much energy so quickly, it's using a more advanced recipe. There's a historical quirk here too. For decades, scientists debated how stars actually fused hydrogen. It wasn't until the 1930s that Hans Bethe figured out the CNO cycle. He won a Nobel Prize for it in 1967. Before that, it was guesswork and equations scribbled in chalk-stained offices. Historians still argue whether Bethe should have shared that prize with others, like Carl von Weizsäcker, who independently described similar ideas. But science, like stardust, often scatters credit in strange directions. Back in the core, things aren't peaceful. Fusion creates radiation pressure that pushes outward, battling the star's own gravity. And above that, a thick shell of plasma churns and swirls in convective loops, boiling currents of charged gas that carry heat up to the surface. This convection zone acts like a lava lamp with a death wish. Hot plasma rises, cools, sinks again, rises. It's slow-motion turbulence on a scale your brain refuses to process. If you could dip your hand in, spoiler, you can't, it'd be like pressing into the sunniest part of a furnace made of knives. These loops shape everything. Surface ripples, star spots, even massive stellar flares, sudden explosions of energy that can outshine the entire star for brief moments. And sometimes, the loops tangle. Magnetic fields twist, snap, and release bursts of radiation. You know how Earth has solar storms that mess with GPS and power lines? Yeah, imagine that, times a billion. If Earth got caught in one of this star's flares, we'd go full blackout before you could say, "Where'd the moon go?" And yet, it's all perfectly natural. You watch this delicate balance, the battle between gravity pulling in and fusion pushing out, and you wonder, how does it not fall apart? Well, sometimes it does. Stars this massive are prone to what astronomers call instability. They bloat, shrink, pulse. Some even eject massive chunks of their outer layers, what's known as stellar mass loss. In extreme cases, they might lose the equivalent of several Earths' worth of material every single year. It's like someone's peeling the star like a cosmic onion. That's partly why your 200,000 degrees Celsius monster is so hot. It's lost much of its outer envelope, the cooler layers, leaving only the roaring hot interior exposed. This is what earns it the Wolf-Rayet label. You're seeing the core, naked and furious. And while it might seem like these stars are short-tempered, they're actually extremely delicate systems. A tiny imbalance, just a small temperature change or a misalignment in fusion rates, can trigger catastrophic collapse. Still, for now, your star holds. It keeps fusing. Keeps shining. You drift upward again, watching the heat ripple through the star like pressure waves through a cauldron. You feel like you've just toured a nuclear reactor built by ancient, invisible hands. There's a little-known tidbit here. Some early theories in the 1800s proposed that stars shine due to gravitational contraction, that they were slowly shrinking, releasing heat. Fusion wasn't even on the radar yet. The discovery of radioactivity briefly derailed those ideas. Some scientists thought stars might be giant radioactive chunks, glowing from internal decay. Charming. Incorrect. But charming. Now we know better. Now you've seen it, up close, in all its burning glory. Fusion. Balance. Fury. You float once more above the surface of your star. The glow is intense. The silence, even more so. You realize, this entire system, this deadly, beautiful thing, runs with perfect efficiency. For now. You hover just above the glowing shell of the star now, its so-called surface. But here's the thing, it doesn't have a surface. Not like Earth. Not even like a gas giant. You can't land on a star. There's no ground. No crust. No satisfying thump when your feet hit something solid. Just layer after layer of superheated plasma, getting thinner and more transparent the farther you drift outward. What you're seeing is the photosphere, the point where light finally escapes into space. It's not a solid wall. It's more like the edge of a cloud, a blurry skin of photons being born and flung out at the speed of light. Still, to your eyes, it looks like a surface, smoothish, glowing, and deceptively calm. You know it's not. This is where the star's deep chaos becomes visible. Every bubble, ripple, and flare you see is a message from deeper down, like watching the surface of soup to guess what's happening at the bottom of the pot. And it's boiling. You start to spot strange patterns, massive loops of plasma rising and falling, each one bigger than Earth. They shimmer with magnetic energy, glowing in ultraviolet and X-ray light. Some rise hundreds of thousands of kilometers before collapsing back into the furnace. These loops are coronal arches, think of them as magnetic trapdoors, flinging charged particles into orbit before snapping shut again. And then there are the star spots. Yes, sunspots, but way worse. Patches where the surface cools slightly due to magnetic interference. Cooler, in this case, means a mere 100,000 degrees Celsius instead of 200,000 degrees Celsius. Practically chilly. The contrast makes them visible, giant dark splotches drifting lazily across the star's surface, like bruises on an angry fruit. In 2013, astronomers discovered starspots on stars even larger than this one using ultrasensitive light curves from the Kepler Space Telescope. These aren't harmless blemishes. They signal instability, warning that the star is wobbling towards something big. Something loud. Historians still argue whether the black fires recorded in early Arabic star charts were primitive descriptions of sunspots, or hallucinations from staring at the sky too long. But whatever they were seeing, they were right to be uneasy. Big stars don't spot up without reason. And the turbulence doesn't end at the surface. Above the photosphere lies the chromosphere, and above that, the corona, an extended outer atmosphere that's hotter than the surface itself. Yes, hotter. That's not a mistake. The surface might be at 200,000 degrees Celsius, but the corona can reach into the millions. It's like wearing a coat made of lava that gets hotter the farther it is from your body. Scientists still don't fully understand why. It's called the coronal heating problem, and it remains one of the weirdest unsolved mysteries in astrophysics. Some blame magnetic waves. Others suspect tiny nanoflares that pop like cosmic bubble wrap. Either way, the corona is nuts. And it's enormous. It extends for millions of kilometers, a shimmering halo of plasma that bleeds into space. It's faint, but deadly. Earth's magnetic field and atmosphere protect us from our sun's corona, barely. But if you stood near this star's corona, you'd be deep-fried, vaporized, and then lightly toasted just for good measure. You drift sideways now, watching as stellar prominences twist into space, massive arcs of plasma hurled upward, then pulled back by magnetic tethers. Some break free entirely, becoming coronal mass ejections, CMEs, that race outward, carrying billions of tons of stellar material. These events can be larger than Jupiter. In fact, a single CME from a hypergiant could engulf entire planets. If one were aimed at Earth, we'd be offline, in the dark, and back to writing by candlelight before you could tweet about it. You think back to 1859, the Carrington event, when a solar flare from our calm little sun disrupted telegraph systems across Europe and North America. Imagine that times 1,000. Your star doesn't cause blackouts. It causes extinction events. And yet, it's all so hypnotic. You float near one of those prominences and watch it arc, glowing crimson and orange, humming like a giant tuning fork. There's a rhythm here. A music. You can almost hear it, if only space weren't so cruelly silent. Early 20th century astronomers used spectroscopy to decode this music, splitting starlight into its component colors to learn about its composition. And when they trained their instruments on stars like this, they saw wild, broad emission lines, signatures of helium, carbon, and even neon, all swirling in impossible amounts. These stars aren't just hot. They're chemically exotic. You spot a flicker, brief, but unmistakable. A small explosion on the surface. Not a flare, not a prominence. A pulse. Stars like this sometimes undergo pulsational instability. They literally beat, like hearts. Not in a cute way. More like someone slapping a water balloon with a tennis racket. It expands, contracts, and sometimes, if the rhythm gets bad enough, it bursts. This isn't happening now. But you can feel it coming. The heat. The imbalance. The mounting energy. And all of it, every ripple and flare and undulation, is happening in a space with no solid form. It's a reminder, the universe doesn't owe you a surface to stand on. Sometimes, the most powerful things are made entirely of pressure, heat, and light. You float away slowly, letting the full spectacle sink in. This star has no edge. No floor. Just boundaries defined by physics and imagination. And yet, it feels alive. You drift a bit farther from the star now, not because you're safer here, but because you're about to learn the truth about its glow. That soft blue shimmer you've been admiring. It's not soft. It's not even friendly. It's lethal. See, when you feel sunshine on your skin, you're getting a warm hug from a very chill star. Most of that warmth comes in the form of visible light and a bit of ultraviolet. It gives you life. It gives you tan lines. And if you're unlucky, it gives you sunburn. But this star. It doesn't give you a sunburn. It gives you immediate molecular damage. The light from this 200,000 degrees Celsius monster isn't just bright. It's jam-packed with ionizing radiation, ultraviolet, X-rays, and gamma rays, the kinds of light that rip electrons off atoms and turn your DNA into abstract art. You're looking at the difference between a cozy fireplace and a nuclear detonation. The light isn't just illumination, it's energy so condensed, so aggressive, it physically alters matter. Imagine holding a book near a campfire. It might warm up. Now imagine holding that same book next to a rocket launch. It doesn't warm up, it ignites. Vaporizes. Ceases to be a book. That's the difference in radiation. And your imaginary self? If you weren't in some dreamy safety bubble, your atoms would have already voted to scatter. Your eyes? Instantly gone. Your skin? Turned into high-speed steam. Your insides? Cooking from the inside out, courtesy of high-energy photons blasting through you like cosmic buckshot. Still feeling brave? You watch as radiation pours off the star in every direction. It travels forever, uninterrupted unless it slams into something unlucky, like a planet, a spacecraft, or a nearby gas cloud. And when it does hit something, it changes that thing. Radiation from stars like this ionizes gas, stripping electrons and lighting up nebulae in glorious, deadly color. It drives chemical reactions that might otherwise take eons. It reshapes atmospheres. It sterilizes entire star systems. This is why life as we know it could never evolve near a star like this. Not on any planet close enough to feel its light. The radiation would erase organic molecules before they could finish saying RNA. You float past a phantom planet now, imaginary, just for perspective. It's orbiting your star at a distance farther than Earth is from the Sun. But even here, it's getting hammered by high-energy light. Its atmosphere is stripped. Its surface glows faintly from chemical trauma. No oceans. No clouds. Just glassy rock and scorched regret. And yet, somehow, things still try. There are planets out there, rogue survivors, that orbit massive stars. Some even form in their debris disks. But they live fast and die young, either consumed by the star's death throes or ejected from the system entirely. Astronomers once found a planet orbiting KELT-9, a star with a surface temperature of about 10,000 degrees Celsius. Not nearly 200,000, but still way hotter than our Sun. That planet's atmosphere is literally boiling off into space. Scientists call it ultra-hot Jupiter. Imagine living there. You'd need sunscreen with a nuclear reactor rating. Radiation isn't just a nuisance. It's the defining feature of this star's personality. You remember learning in school that light travels in waves: radio, microwave, infrared, visible, UV, X-ray, gamma. This star doesn't bother with the long, lazy stuff like radio waves. It jumps straight to the killer bands. Gamma rays are the top of the spectrum, pure violence in wave form. They pass through matter like it's not even there. On Earth, we need lead shielding just to survive a few minutes of exposure. This star is cranking out gamma rays like confetti at a parade. Still, there's beauty here. You watch as the star's stellar wind, a stream of charged particles, meets the surrounding interstellar gas. The collision creates a shockwave, glowing faintly in X-rays. This is called a bow shock, and it looks like a ripple of blue fire curving out into the void. In 2012, NASA captured images of Zeta Ophiuchi, a hot runaway star, with a similar shockwave. That star was fleeing its home system at 24 kilometers per second, because its binary companion had gone supernova. And it left a glowing X-ray arc in its wake, like the trail of a comet with anger issues. Historians still argue whether ancient observers ever noticed this radiation's indirect effects. Some link sudden crop failures or animal migrations to unseen cosmic rays. Others say it's coincidence. But the stories are there, vague, unnerving, oddly timed with celestial events. Back at your star, you start to feel overwhelmed. Not emotionally, physically. Your fantasy shield flickers as the radiation intensifies. You're bathing in pure energy, and your imaginary senses are on fire. Not pain, exactly. More like a buzzing. An ache in the idea of having a body. You float farther back, letting the glow fade a little. And suddenly, you're grateful for Earth's magnetic field. Its atmosphere. Its ozone layer. You think of all the gentle protection that filters out the sun's harsher rays, and you realize just how spoiled you are. Life on Earth thrives not because the sun is powerful, but because it's restrained. This star is all unfiltered rage. Even now, astronomers are building detectors in space and underground to monitor these types of radiation. Not just for science, but for survival. A single high-energy flare from the right kind of star could fry satellites, blind sensors, and ruin weeks of internet history. And this one? It's the template. The worst-case scenario. The radioactive supermodel of space. You stare at the glow one last time, beautiful, blue, and utterly unforgiving. A star like this doesn't warn you. It warns you. You drift quietly now, in the long orbit just beyond the reach of madness. The light behind you glows brighter than anything your mind can process, and still, it's just a star. A single object. A single engine of fusion, heat, and pressure. But what if it wasn't alone? Here's where things get strange. Stars like this, massive, rare, furious, don't always live solitary lives. In fact, many are born into multiple star systems, tangled up with one or more stellar siblings. And when your main character is a 200,000 degrees Celsius blue hypergiant, you can bet its family dynamic is complicated. You ease toward a ghostly companion now, imaginary, again, but inspired by real astrophysical cases. A second star, smaller, dimmer, but gravitationally tethered. Caught in a cosmic waltz. This isn't a graceful ballroom spin, though. It's more like dancing on a volcano during an earthquake. The two stars orbit each other in an elliptical loop, their gravitational field stretching space like rubber. Every pass gets a little closer, a little more dangerous. Sometimes, the smaller star is close enough to feel the outer winds of its giant partner. Material begins to flow between them. Not air. Not gas. Plasma. Superheated, magnetized, and angry. The larger star is literally feeding the smaller one, or vice versa, depending on who's more bloated and unstable at the time. This process is called mass transfer, and it's as dramatic as it sounds. The stars distort each other into stretched, teardrop shapes. Gas flows along the gravitational path called the Roche lobe, spiraling into the companion and forming a swirling accretion disk. Imagine watching one star bleed into another. This exchange can make the recipient star grow hotter, brighter, even spin faster, like throwing logs onto a fire that's already out of control. In some extreme cases, the spinning reaches breakup speed. That's when the star's equator starts to fly off in chunks. Stellar meat grinder, anyone? You pause to consider, could our 200,000 degrees Celsius star have a companion like this? It's possible. Wolf-Rayet stars, the hot stripped cores of massive stars, are often found in binaries. Some famous systems, like WR104, show massive spiral patterns of dust and gas, evidence of two stars dancing and shedding material in perfect spirals. And that's the thing, those spirals aren't just pretty. They're warnings. They show that energy is being lost. Angular momentum is leaking. The stars are spiraling inward, slowly, inevitably. Like two ice skaters pulling into a deadly spin they won't walk away from. If the stars get close enough, one of two things happens. They merge, becoming a single, unstable, ultramassive star that is practically guaranteed to explode violently. They collide and trigger a supernova prematurely, blasting apart before either had the chance to die on their own. And in some bizarre, extreme cases, the explosion is asymmetric. A single lopsided detonation that kicks one star out of the system at absurd speed, creating a hypervelocity star, flung across the galaxy like a bullet. One such star, US 708, is racing through the Milky Way at over 1,200 kilometers per second, fast enough to leave the galaxy altogether. Its origin story? Likely a binary partner to a white dwarf that exploded in a Type Ia supernova. Stellar heartbreak with literal fallout. Historians still argue whether the wandering stars mentioned in Babylonian tablets were attempts to track these rare events, or simply early records of fast-moving planets. But something tells you the ancient skywatchers noticed more than they could explain. Back near your hot giant, you glance sideways at your phantom companion star again. The space between them pulses with radiation. Jets of material erupt, linking the two with glowing arcs like lightning bolts frozen mid-flash. Binary systems like this aren't just volatile. They're astronomical laboratories. Because the dance of dual stars lets scientists measure things we can't observe directly: mass, composition, energy output. When one eclipses the other, the light dips. When they orbit, the spectrum shifts. These tiny wobbles and flickers are goldmines of data. But more than that, they hint at the star's future. Massive binaries often end in double death, two supernovae, followed by two neutron stars, or even two black holes. And if those black holes are close enough, they eventually spiral together, colliding in a gravitational wave event that ripples through the universe like a deep bass drum you feel in your bones. One such ripple was detected in 2015, GW150914, the first confirmed gravitational wave. It came from the merger of two stellar mass black holes. The energy released in that single moment was greater than the light from all the stars in the universe, combined. All from two stars, once orbiting each other. Probably hot. Definitely doomed. You look back at your 200,000 degrees Celsius friend and feel the weight of that knowledge. Even in company, it's not safe. Maybe especially in company. Companionship, for stars this extreme, isn't warmth and comfort. It's a ticking clock. You drift farther into the cosmic dark now, letting the star grow smaller behind you, not because it's any less fascinating, but because its future is starting to rumble. And it's not going to be pretty. You see, stars this massive don't age like the sun. They don't quietly dim and puff into red giants. No, they collapse, explode, and shatter the silence of space in ways that leave entire star systems permanently changed. This star, your 200,000 degrees Celsius fire demon, is approaching a chapter it won't survive. Its death won't be gentle. It won't be poetic. It will be cataclysmic. Inside, the core has been fusing elements rapidly. First hydrogen into helium. Then helium into carbon. Then carbon into oxygen, neon, magnesium, silicon. And finally, the ultimate dead end, iron. Iron is the cosmic wall. It's the element that kills stars, not because it's dangerous by itself, but because it takes in more energy than it gives back. Fusion stops being profitable here. The star's core reaches a point where it can no longer support its own weight. The moment iron dominates the core, gravity wins. The collapse is swift, milliseconds swift. The core folds in on itself, slamming protons and electrons into neutrons. The outer layers? They don't get the memo in time. They're still falling. They slam into that ultradense core and bounce, triggering the most violent explosion the universe allows a star to have. A core collapse supernova. This is the moment where your peaceful orbiting ends. Even from far away, your imaginary ears are filled with a silent scream: radiation, light, shockwaves, and a burst of neutrinos so vast, they stream through entire planets without ever hitting anything. This explosion is so bright it can outshine an entire galaxy, for weeks. It releases more energy in a few seconds than the Sun will in its entire 10 billion year lifespan. There's historical precedent here. In 1054 CE, Chinese and Arabic astronomers recorded a guest star in the sky, bright enough to be seen during the day. Historians now know it was a supernova, the death of a massive star in the Crab Nebula. Still debated whether early European records mention it at all. Some say church scholars ignored the event, fearing it contradicted religious cosmology. Others think it simply wasn't seen due to bad weather. Either way, the star died, whether anyone noticed or not. Your star is going to die like that. But louder. Depending on its mass at the moment of collapse, it may do something even worse. It may form a black hole. If the collapsing core is too massive to be held up by neutron pressure, it implodes past the point of no return, warping spacetime into a bottomless well. The newly born black hole begins eating its surroundings, devouring the inner regions of the star as the outer layers explode outward. In rare cases, this can trigger a hypernova, a supernova's unhinged older cousin. Even more energy. Even more radiation. The explosion might spawn gamma-ray bursts, intense beams of energy that scream through space at light speed. If one of those beams hits a nearby planet, it's a mass extinction event, guaranteed. A single gamma-ray burst could strip Earth's ozone layer and bake the surface with UV light. Luckily, there are no hypergiants nearby. That we know of. Back at the dying star, you're now witnessing the aftermath. Shockwaves ripple out in every direction, slamming into the surrounding gas and dust. This creates a glowing supernova remnant, a nebula of hot, ionized debris expanding outward for tens of thousands of years. You've seen these before in photographs, the Veil Nebula, the Crab Nebula, the hauntingly intricate Cassiopeia A. All are the echoes of dead stars. And in the center of that wreckage? If it didn't become a black hole, it left behind a neutron star, an object so dense, a teaspoon of it would weigh 1 billion tons. It might spin rapidly, sending out beams of radiation like a lighthouse. These are called pulsars, and they're among the most precise clocks in the universe. Imagine a spinning core, 20 kilometers wide, rotating dozens or hundreds of times per second. Every tick a signal from a star that once burned at 200,000 degrees Celsius. That's legacy. But here's where it gets even more interesting. All the elements forged during the star's lifetime, and during the explosion, are now free. Iron, nickel, gold, uranium. These heavy elements scatter into space, seeding future clouds, planets, and life. You, in a very literal sense, are made of star stuff. But not just any star. You're made of dead giants. Hypergiants. The rare ones that lived fast, burned hot, and died loud. There's a beautiful fringe theory that the heaviest elements, like gold and platinum, require not just supernovae, but neutron-star collisions, which often begin with massive binary stars dying side by side. So the jewelry you wear might have started as two blue hypergiants, billions of years ago, dancing, dying, and then fusing in a final death spiral. You look now at the expanding cloud left behind by your hypergiant. It glows in false colors, X-rays, visible light, and radio waves. Over time, this will spread across light years, shaping the galaxy around it. Some of that dust will cool, settle, clump. Some will form planets. Some might form you. From fire to dust to thought. Not bad for something that began as a howling gas cloud. The star is gone now. All that's left behind is a ghost, a glowing shell of wreckage drifting through interstellar space, cooling slowly, whispering its death across millions of kilometers. And you? You're still here, floating, watching the remains settle into silence. But the story isn't over. Not by a long shot. Because even in death, this star keeps changing the universe around it. You look around, and something starts to shift. The space near the exploded hypergiant is no longer empty. It's filling with chemistry. Swirling gases, rich with carbon, oxygen, iron, silicon, all shaken loose by that final collapse. This is where the next generation of stars and planets begins. The explosion seeded the region with all the complex elements needed for rocky planets, for atmospheres, for oceans, and, eventually, for life. You're witnessing a cycle, death feeding birth. Destruction creating possibility. You remember what astronomers call it, stellar nucleosynthesis, the idea that every element heavier than hydrogen and helium was cooked inside stars like the one you just watched die. In fact, over 90% of your body, calcium in your bones, iron in your blood, oxygen in your breath, was forged in a star that exploded long before Earth even existed. You're not just stardust. You're recycled hypergiant ash. The wreckage begins to cool and condense. Slowly. Gently. It doesn't look like much now, just gas and dust drifting through space, but given a few million years, it'll become something again. You watch as gravity starts to regroup. Clumps of dust begin to swirl, attracted to each other. Larger and larger blobs form. And here's where it gets beautiful. Some of those blobs will become stars. Smaller ones this time, more stable, like our sun. Others will flatten into disks, spinning and gathering debris until planets form. Some rocky. Some icy. A few just right for liquid water. One or two of them, maybe, just maybe, will sprout trees, fish, laughter. Consciousness. They'll build stories. Languages. Microwaves. And maybe even telescopes, pointed back toward the stars. They'll wonder where it all began. And they'll never guess it started with a monster. Historians still argue whether early creation myths, like those of the Dogon people of Mali, who spoke of star companions and invisible forces, were metaphorical or based on ancient celestial observations. Did they know about stellar death? Probably not in our terms. But the intuition was there. Something immense, something powerful, always dying and being reborn. You now drift closer to one of those new forming stars. It's still embryonic, hidden inside a cocoon of dust. Radio telescopes on Earth can detect these, protostars, glowing faintly as they gather mass. Maybe it will live a long, quiet life. Maybe it will explode someday too. You won't know. Not in this lifetime. But the legacy of your 200,000 degrees Celsius hypergiant lingers everywhere. Every atom it forged is a seed. A gift. A cosmic inheritance. And speaking of inheritance, here's something strange. Some of the elements from that dead star won't get recycled into planets at all. They'll become part of cosmic rays, high-energy particles flung across the galaxy at nearly the speed of light. These particles zip through space, through atmospheres, and even through you, every second. Yes, you. Sitting there. Right now. There's a decent chance one of those particles came from a hypergiant star that exploded millions of years ago. A tiny hello from the past, tapping your atoms with a whisper, I burned. I died. And now I'm passing through you. Science can't predict exactly which hypergiant exploded where. But the timelines make sense. Cosmic rays take hundreds or thousands of years to reach us, often deflected or slowed by magnetic fields. Some are trapped in our atmosphere. Some slam into spacecraft. Some, no joke, leave tiny trails in photographic plates, which scientists use to study their speed and composition. They are fingerprints from stars long dead. And sometimes, those fingerprints show something new. A heavy isotope we've never seen before. A super-heavy element that only forms in supernovae or neutron star collisions. Every time we find one, it's like reading a page of a cosmic diary written in plasma and pain. You pause and think, this one hypergiant, this one impossibly hot, short-lived creature, has spread itself across space in so many ways. Milky Way as nebulae, high voltage as radiation, collision as shockwaves, DNA and as atoms riding on the wind. And through all of this, it has changed you. Not just metaphorically, but physically. You carry pieces of stars inside you. You are the legacy of violence and beauty. It's a strange comfort, isn't it? To know that the most terrifying thing in the galaxy, the one you couldn't survive even for a second, might also be the reason you exist at all. You find yourself staring back toward the expanding cloud of stellar remains, but now your attention shifts, not to what's visible, but to what's moving through the invisible. Because while the light show fades, the gravitational story is just beginning. The star is dead, yes, but its weight. Its mass. Still here. Still twisting spacetime. You drift toward the aftermath center. If this one collapsed into a neutron star, you'd be approaching a sphere 20 kilometers across but with more mass than the sun. You wouldn't see much, just a tiny, spinning object, beaming focused radiation like a cosmic lighthouse. But what if it collapsed even further? What if the core crossed the Schwarzschild radius, the point of no return, and became a black hole? Then all bets are off. You feel it before you see it. The way space bends. The way time seems to slow. You don't hear a sound, but your whole imaginary being knows something enormous is nearby. And there it is. A black hole. Born from a star too hot, too massive, too unstable to survive its own existence. It doesn't glow. It doesn't scream. It just erases. A perfect sphere of darkness surrounded by a glowing accretion disk, gas and dust spiraling inward, heating up to millions of degrees as it falls, lighting up X-rays before vanishing past the event horizon. This isn't science fiction. This is real. We've seen it. In 2019, astronomers used the Event Horizon Telescope to capture the silhouette of a black hole in the galaxy M87. That orange donut? That's the ghost of infalling light. The black center. That's where reality folds. And while M87's monster black hole is far larger than anything a single star can create, stellar mass black holes, like the one in front of you, are everywhere. Formed by deaths like the one you just watched. Here's something wilder: if your 200,000 degrees Celsius star had a binary companion, and both stars collapsed into black holes, they might one day spiral into each other and merge. The result? A bigger black hole, and a ripple of gravitational waves across the cosmos. These waves are tiny, like stretching a ruler by the width of an atom, but we can detect them. Instruments like LIGO and Virgo pick them up, letting us hear collisions between invisible monsters. Historians still argue whether Einstein ever truly believed gravitational waves would be measurable. He predicted them in 1916, but in later letters, he expressed doubts. He couldn't have imagined we'd one day build machines that catch the tremors of spacetime itself. You pull back now, watching how the dead star's gravitational fingerprint continues to shape its surroundings. Nearby clouds of gas collapse toward the black hole, feeding it slowly. Stars that drift too close get spaghettified, stretched into long streams of plasma before being devoured. The black hole grows. Quietly. Powerfully. It becomes the anchor of a new gravitational neighborhood. And here's the kicker: black holes don't just destroy. They influence. They sculpt. They even spark creation. The jets that erupt from some spinning black holes can blast matter into space at near light speeds. This injected energy can compress nearby clouds, helping trigger the birth of new stars. So yes, something that once destroyed everything in its reach can also cause stars to form. You feel that deep contradiction settle into your bones. Life. Death. Creation. Collapse. All swirling together. Some fringe physicists even propose that black holes might contain baby universes inside them. That every collapse spawns a new Big Bang somewhere else. It's unproven, sure, but the idea that destruction here leads to birth there. It's a poetic echo of the universe's strange logic. Even stranger, in 2022, researchers detected what they think might be the birth cry of a black hole, a sudden drop in X-rays followed by a rising pulse, possibly the moment the event horizon formed. We're not just theorizing anymore. We're watching it happen. And this one, the star you've been following from furnace to fallout, it might still be whispering across space in ways we can't yet hear. You float back, slowly now, watching the black hole spin in eerie silence. Its accretion disk flickers like a halo of trapped light. And all around it, the galaxy goes on, stars drifting, planets turning, clouds coalescing. The universe doesn't pause for grief. You wonder, how many stars in the sky are just waiting to die like this? How many of them have already gone dark, their light still on the way? The night sky might be full of ghosts, beams of photons from stars that exploded centuries ago, their images still arriving while their bones drift silently through space. You think of your own star now. Not the hypergiant, but the one you're under every day. The sun warm. Stable. Predictable. For now. It, too, will die. But not with violence. With a sigh. In about 5 billion years, it'll swell into a red giant, puff away its outer layers, and leave behind a quiet white dwarf, a glowing ember, no explosions, no black holes. Just a memory. You're lucky. You were born near a calm star. You were not built to survive a 200,000 degrees Celsius inferno. But somehow, that inferno built you. You're floating now in a region that once held a fireball of raw destruction, and yet, it's gone quiet. Not empty. Not lifeless. But quiet in the most profound, echoing sense. The star you followed, your ferocious, 200,000 degrees Celsius companion, is now a gravitational scar in space. Its story may be over, but its influence still unraveling. And now, we turn our gaze outward. Beyond the wreckage. Beyond the debris. Beyond the reach of its light. Because this star didn't just change its neighborhood. It changed the galaxy. You drift back, wider and wider, until you can see how stellar feedback from giants like this one helped shape galactic arms. The supernova explosion you witnessed wasn't just an end, it was a trigger. Massive stars inject energy, momentum, and heavy elements into their surroundings. And that does something extraordinary, it regulates star formation. Too many stars forming too quickly. A hypergiant explodes and pushes gas away, slowing down the chaos. Too few. Its shockwaves can compress clouds, igniting new bursts of creation. It's like galactic breathing: inhale, stars are born; exhale, giants die, clearing the air. Your star's death may have cleared a whole patch of interstellar medium, forming cavities known as superbubbles. These structures, invisible in optical light but glowing in X-rays, are carved by overlapping supernovae. You're now floating through one. In our own Milky Way, Earth sits within such a void, the local bubble, thought to be the aftermath of multiple ancient supernovae, some maybe 10 million years old. We're literally living in a neighborhood that used to be a war zone. Historians still argue whether early myths about sky winds or the breath of the gods were poetic hints at these unseen forces. The idea of invisible, powerful currents shaping creation, it's older than telescopes. Maybe they weren't so far off. You turn now to the larger ecosystem. Massive stars like the one you follow belong to a strange caste in the galaxy. They're few, but they're the architects of everything. They only live for millions of years, compared to billions for smaller stars. And yet, their brief lives inject the galaxy with all the ingredients needed for complexity. Astronomers have tracked these effects using spectroscopy, mapping regions enriched by stellar death. They see oxygen trails, iron pockets, and carbon dust drifting between star systems, each traceable back to a specific type of supernova. Some of this dust becomes planets. Some becomes comets. Some just floats forever, waiting for gravity to find it again. And speaking of dust, you zoom in now on a smaller pocket, one that escaped the black hole's pull. It's cooling, clumping. It's forming organic molecules. Complex ones. PAHs, polycyclic aromatic hydrocarbons, the same basic structures found in Earth's earliest life forms, can be found in space. Around stars. Inside nebulae. Even within meteorites. It's as if life, or at least its blueprint, is sprinkled everywhere by stars like this one. You imagine a future where that material lands on a quiet planet, mixes with water, and after a billion years or so, wonders where it came from. The answer? A star you couldn't have survived. But now, let's flip things again. What if your hypergiant had lived in a different kind of galaxy? Not a spiral like ours, but an elliptical galaxy, crowded and old. There, it may have burned even faster. Exploded sooner. Left behind debris that was quickly swallowed by other stars. Or in a dwarf galaxy, where every massive star's death has an outsized effect. A single hypernova might sterilize an entire region, sending radiation across half the galaxy. Some galaxies even go through starburst phases, wild, chaotic periods where stars form by the thousands, and die just as quickly. Hypergiants like yours become common. Explosions happen weekly. The whole place lights up in X-rays and radio waves, like a fireworks show that never ends. And somewhere out there, no joke, there may be galaxies with even hotter, shorter-lived stars. Population 3 stars, the first stars ever formed after the Big Bang, may have burned hotter than anything alive today. Maybe even over 300,000 degrees Celsius. We haven't found one yet. But their ashes? We've seen those. They laid the foundation for every star that came after. Including yours. Including you. So while your 200,000 degrees Celsius monster might seem like a rare, one-off freak of nature, it's not. It's part of a family. A cycle. A system. You're starting to see the picture now. Not as separate pieces, light, heat, gravity, atoms, but as one enormous pattern. Woven by time. Rewritten by death. Built by pressure. Every photon this star ever emitted is still flying outward. Every particle it flung into space is still moving. The energy it released didn't vanish. It just spread. That's what stars do. They shine. They die. They echo. You're still drifting in space, further and further out, the memory of that hypergiant now reduced to a faint shimmer in your imagination. And as you drift, something begins to dawn on you. This star, the one that once blazed at 200,000 degrees Celsius, was more than just a curiosity. It was a benchmark, a limit tester, a freak of cosmic engineering. So let's ask a daring question. Could anything be hotter? Hotter than a hypergiant burning brighter than physics should allow? Hotter than fusion-powered madness held together by pure gravity? The answer? Surprisingly, yes. But the answers aren't simple, and they aren't stars. You start by looking at other objects in the stellar zoo. Your hypergiant, impressive as it was, burned at 200,000 degrees Celsius on its surface, but inside? Even higher. Stellar cores often reach tens of millions of degrees Celsius. That's fusion territory, where atoms slam together and release energy. But there's an even more extreme class, supernova cores during collapse. In the moment a massive star collapses, its core can spike to 3 to 5 billion degrees C, briefly. The pressure, density, and temperature all skyrocket as gravity crushes everything inward. But these temperatures don't last. They're a transitional moment, a cosmic snap, not a stable state. So technically, yes. A supernova's dying heart gets hotter than your hypergiant. But it dies seconds later. Still, you're not satisfied. You want longer-lasting monsters. So you head to something weirder, accretion disks around black holes. Here's where things get absurd. When gas spirals into a black hole, it forms a thin, hot disk, like a flaming ring around a drain. And because this matter is moving near light speed, it heats up through friction and gravitational compression. Some regions of these disks can reach 100 million to 1 billion degrees C. Let that sink in. You're looking at temperatures 5 to 50 times higher than the core of the Sun. And this isn't theoretical, we've detected these disks in X-rays, their glow so intense that telescopes like Chandra and NuStar can barely keep up. Then there are neutron stars, those crushed stellar cores left behind after supernovae. Their surfaces can reach 1 million degrees C, but their interiors? Even hotter. And here's the wild part, they don't shine like normal stars. Their heat is mostly locked inside, leaking out slowly over billions of years. Some neutron stars even have magnetic fields so strong, they distort atoms. These are called magnetars. Their magnetic fields are trillions of times stronger than Earth's, and their crusts sometimes quake, releasing energy equivalent to a solar flare in under a second. In 2004, one magnetar called SGR 1806-20 had a quake that lit up the galaxy for a moment. For a fraction of a second, it outshone the entire Milky Way. Historians still argue whether such bursts were ever noticed by early civilizations, maybe as mysterious flashes in ancient records, or even as causes for sudden navigational errors. The evidence is shaky. The mystery remains. But let's step away from known stars entirely. Let's talk man-made heat. On Earth, at the Large Hadron Collider, scientists have created temperatures of over 5.5 trillion degrees C, yes, trillion, by smashing lead ions together. For a brief moment, they created a quark-gluon plasma, the state of matter thought to exist right after the Big Bang. So in that moment, a machine on Earth outheated every star ever born. But again, it didn't last. It existed for yoctoseconds, that's 10 to the power of negative 24 seconds. Which brings you back to your hypergiant. Yes, it wasn't the hottest thing in the universe. But it was stable, sustained, and visible from galaxies away. It lived, it breathed, and it changed everything around it, permanently. No supernova, no collider burst, no disk of gas around a black hole will ever write its story in the sky quite like a burning star. But, what about the endgame? Is there a theoretical ceiling? A cosmic maximum? According to some physicists, there is, the Planck temperature, the highest possible temperature in the universe. It's around 1.416808 times 10 superscript 3 superscript 2 Kelvin. That's a number so big, it basically breaks physics. At that temperature, the laws of spacetime no longer apply. Gravity, quantum mechanics, thermodynamics, they all collapse into one frothing, chaotic soup. It's believed this temperature may have existed a fraction of a second after the Big Bang, and never since. You're hypergiant. A flicker by comparison. But here's the twist. Even though it wasn't the hottest, it's the kind of heat we can understand. We can study it. Photograph it. Watch it evolve. It tells us where we came from. It lights the road to where we're going. And unlike the Big Bang or a magnetar quake, it speaks in visible light, the one part of the spectrum we humans are built to see. That alone makes it feel hotter, more immediate, more terrifying. Because it's real, and you could point to it in the sky, if it weren't already long gone. The star you've been following was a limit pusher. One of the hottest naturally occurring objects to ever sustain itself in the universe. Not the absolute hottest. But the most beautifully, dangerously alive. By now, you've traveled far. Not just across light years of space, but across layers of understanding, from birth to death, from heat to gravity, from ancient starlight to atoms in your bones. And yet, somehow, the story of that 200,000 degrees Celsius hypergiant keeps unfolding. Because stars like this leave behind more than just nebulae and shockwaves. They leave behind legends, in data, in language, in culture. You're about to discover how a single star, too distant for survival, too hot for comfort, becomes woven into the minds and myths of a planet filled with humans. Let's start with the science. That's where it always begins now. Astronomers love to catalog things, stars, galaxies, quasars, exoplanets. They build databases filled with designations, HD, WR, BD, SN. Numbers and letters. Clinical. Precise. The star you've been imagining might exist in one of those catalogs. Maybe it's called WR102 Ka, nicknamed the Peony Nebula star, one of the hottest known stars, with surface temperatures reaching close to 200,000 degrees Celsius. It sits quietly, smoldering in infrared, hidden by dust, detectable only by specialized telescopes like Spitzer. And yes, it's real. But that's not what most people remember. People remember what they can feel. And here's where things turn cultural. Throughout human history, stars have been painted into gods, monsters, prophecies, warnings. The sky has never just been sky. It has always been story. Ancient Polynesians used stellar positions for navigation across the Pacific. The Dogon people, as mentioned before, described the invisible companion of Sirius before Western astronomers confirmed it. Chinese records tracked guest stars appearing and vanishing, now known to be supernovae. Even today, we look up and still use terms like giant, dwarf, death, birth. And a hypergiant? That word alone sounds mythical. What's fascinating is how modern astrophysics and ancient storytelling often meet halfway. The idea of a star so powerful it sculpts galaxies would have sounded perfectly reasonable to early civilizations. They just used different words. Sky fire. Chariot of the gods. The soul of a warrior. Historians still argue whether Beowulf's dragon, described as a fire-breathing sky serpent, was inspired by a comet or a particularly bright star. A dying one. One that changed shape or color before vanishing. Supernovae can do that. And here's the sneaky part, we still mythologize stars today. We just use science fiction instead of epic poetry. Think about how often stars play a central role in movies, games, books. Superweapons fueled by suns. Alien civilizations orbiting blue giants. Time travel through black holes born of collapsed hypergiants. Characters named Sol, Nova, Sirius, Vega. Even the Death Star isn't just a play on planets, it's named like a celestial object. You, sitting here listening, might never see a 200,000 degrees Celsius star in the night sky. But you've felt its echo in the fiction you love, the symbols you wear, the metaphors you use. You say someone burns bright. You say they're a star. You understand the emotion of stellar power long before you grasp the equations. And now, you do both. The hypergiant you've imagined, whether it's WR102 Ka or something even stranger, isn't just physics anymore. It's poetry with plasma. Thermodynamics wrapped in all. And it's still being studied. Because here's the twist, we don't know everything about these stars yet. Not even close. Their life cycles are short, and that makes them hard to catch in the act. By the time light reaches us, the star might already be gone. The data could be a ghost message, a stellar obituary written millions of years ago. And some hypergiants behave unexpectedly. They brighten. Then dim. They shed mass suddenly. They erupt. They go silent. Some stars, like Eta Carinae, explode in events called supernova imposters, massive outbursts that look like a supernova but don't destroy the star. Just a warning shot. A stellar tantrum. And we still don't fully understand why. These gaps in knowledge aren't failures. They're invitations. Every unanswered question is a chance to look deeper, build better instruments, ask weirder questions. Could there be hotter stable stars than we've found? Could they burn in dwarf galaxies, hidden from our view? Could they exist in different phases of matter, with exotic interiors we've never imagined? Fringe theories abound. Some propose quark stars, even more compact than neutron stars, made of up-down strange quarks. Theoretically hotter than anything we've confirmed. But again, no proof. Just whispers of math. Still, the universe loves surprises. And so do we. So now, as you float beside the memory of a dead star, you realize, it's still giving. Giving questions. Giving wonder. Giving inspiration. In some ancient future, long after humans are gone, maybe someone else, on some distant world, will see the remnant of this hypergiant, detect the trace metals it left behind, and ask the same question. What lived here? You followed this 200,000 degrees Celsius star through life and death, physics and poetry, science and symbolism. Now, you begin your slow return, not to Earth, not quite yet, but toward the bigger picture. Because one question still lingers, tugging at your curiosity like a gravitational pull. What does this one hypergiant tell us about the universe itself? You gaze into the galactic void and start to see the patterns. Everywhere you look, stars are born, burn, and die. Some peacefully, others violently. Your hypergiant, one of the brightest, briefest players, is a fast-forward button on this cycle. It shows us what the universe is capable of at full volume. And in doing so, it tells us something essential: the universe favors extremes. Let's look at that more closely. On the small end, you have red dwarfs, tiny stars that burn cool and slow, lasting for trillions of years. They're quiet, unassuming, the background characters in the cosmic cast. But then you have hypergiants, blinding, bloated, searing hot, their lives measured in millions of years, not billions. They live fast. Die young. Leave brilliant corpses. And the universe seems to say, yes, let's try both. Your star was part of this wild experiment. A test of how hot, how bright, how fast-burning something could be without instantly unraveling. And it nearly did. Many hypergiants are in a constant tug-of-war with themselves. Their radiation pushes outward. Their gravity pulls inward. The balance is so delicate, one small shift can tip the scales. That's why these stars pulse, erupt, change. They're barely holding it together. There's something oddly relatable about that, isn't there? You watch your star again, this time, rewinding it in your mind like a film reel. It starts as a gas cloud. Collapses. Ignites. Roars. Fuses heavier and heavier elements. Then dies, scattering itself across the starscape. And somehow, in that death, creates everything else. That's the bigger truth. This isn't just about one star being hot. It's about how the most violent processes in the universe are required to build complexity. Without the extreme pressures of stellar fusion, you don't get oxygen. Or carbon. Or iron. Without supernova shock waves, you don't trigger new star formation. Without stellar winds, you don't clear out space for planets to coalesce. It takes monsters to make miracles. Fringe theorists sometimes suggest that the universe itself may have evolved to favor these processes, that certain physical constants make life possible only if massive stars live and die in just the right ways. Change the balance between gravity and electromagnetism just a little. No stars. No elements. No life. It's a controversial idea, sometimes called the anthropic principle. Historians still argue whether it's science or philosophy. But in moments like this, floating next to what's left of a cosmic inferno, it suddenly feels real. Because without that one star, that 200,000 degrees Celsius blip in the sky, there might be no gold in your jewelry. No iron in your blood. No silicon in your processor. And no you, sitting here, thinking about it. You drift back farther now, leaving the galaxy behind. From this vantage, the Milky Way looks like a pinwheel of light and dust. And even from here, you can sense it, the way dead stars fertilize the future. Every twinkle is a story in progress. Every dim glow could be a hypergiant in waiting. Somewhere out there, another gas cloud is collapsing. Another freakishly large star is forming. And somewhere even farther, another just exploded. It's happening all the time. It's cosmic agriculture. Destruction as compost. Heat as the first breath of something better. And it never stops. One of the most haunting discoveries in modern astronomy came from observing galaxies like NGC 6946, also called the fireworks galaxy. There, astronomers expected a supernova from a red supergiant. But instead of an explosion, the star just vanished. No boom. No blaze. Just darkness. The leading theory? It collapsed directly into a black hole, skipping the light show entirely. Quiet death. That possibility changes everything. Because now we know not all stars go out with a bang. Some slip quietly into eternal silence, and we may never even know they were there. And that raises one last, unsettling truth. The universe is full of invisible corpses. Stars that lived. Burned. Died. And left behind nothing but a gravitational twitch. You think about that for a long moment. Then you smile. Because while they might be invisible now, they still matter. The star you followed? Maybe it ended in fire. Or maybe it went dark without a whisper. Either way, it gave something to the galaxy. And maybe, just maybe, to you. The memory of your hypergiant now feels like a faded burn mark on your retina, a phantom glow that lingers even after the light is gone. You're floating at the edge of awareness, suspended in this quiet tapestry of cause and consequence. But before the journey ends, let's bring everything into focus, one last time. What does it really mean to be near a star that burns at 200,000 degrees Celsius? It means standing beside the universe in fast forward. You saw it born from a collapsing cloud, vast and cold and ancient. You felt its ignition, hydrogen roaring into helium, gravity squeezed into flame. You hovered just beyond its reach, feeling the unimaginable heat lash out like solar whips. You watched as it aged in fast motion, shedding layers, bulging at the equator, spinning, pulsing, reshaping its atmosphere daily like a celestial tantrum. And when it died, you saw it collapse, explode, scatter. Into clouds. Into metals. Into mystery. You tracked how its legacy spread, forging black holes, nudging star births, peppering space with the dust that might one day become lungs or mountains or poems. And all throughout this journey, you saw that stars are not eternal. Even the most powerful ones, especially the most powerful ones, live on borrowed time. That's why they shine so hard. Your hypergiant lived only a few million years. That's less time than it took Earth's first multicellular life to crawl into the shallows. Less time than it took for mammals to invent fire. But in those short years, that star burned through hundreds of times the sun's mass, blazing a trail through its corner of the cosmos. And in doing so, it rewrote the rules of its surroundings. That's not just a death. That's an authoring. Even in its self-destruction, your hypergiant told a story. It's in the stardust floating in a nebula you passed earlier. It's in the isotopes hiding inside a meteorite somewhere in Antarctica. It's in the strange spikes of radiation picked up by space probes orbiting Saturn. Its fingerprints are scattered like riddles. And maybe, if the timing was right, it's in you. Because every atom in your body heavier than helium came from a star. That's not metaphor. That's thermonuclear history written into your cells. You may not have survived your hypergiant, but you are part of its legacy. And here's where it gets even more mind-bending. What if all of this isn't rare? What if the universe is littered with stars like this, each one a short-lived engine of creation and destruction? What if they're not the exception, but the rule in certain epochs of cosmic history? Scientists believe the first generation of stars, those elusive population 3 stars, were all giants. With no heavier elements to cool them down during formation, they may have grown to hundreds of solar masses. And burned even hotter than your 200,000 degrees Celsius beast. We've never seen one. But their echoes may still ripple through the universe, in the form of ancient black holes and unusual element ratios in old stars. They were here before galaxies had shape. Before Earth. Before the Sun. Before language. They were the original architects. And what you just witnessed may have been a modern echo of that ancient fire. Even now, telescopes like James Webb are hunting the faint red whispers of those first stars. Not the stars themselves, they're long dead, but their aftermath. And every new observation adds another pixel to the portrait. Another note to the symphony. Another verse to the bedtime story. Because that's what this has always been, a story. Told not with words, but with particles and light and shadow. With hydrogen. With iron. With time. You've followed a single spark from ignition to extinction. And in that journey, you've glimpsed what the universe truly is. Not a cold machine. Not a sterile vacuum. But a furnace of transformation. A place where heat becomes hope. Where fire becomes foundation. Where death becomes dust, and dust becomes everything. You. Me. Us. Wind down, final 300 words. And now, as you drift even farther, the heat fades. The radiation softens. The noise of a burning star becomes a memory, hushed, like the crackle of a fire long gone out. You're suspended in the afterglow, weightless, the light of other suns blinking slowly across the dark. Let yourself breathe. Let the pace slow, as the universe does after an outburst of light. You feel the vastness around you, cool now, calm. The violence is over, and what's left is peace. The remnants of that hypergiant, its gas, its elements, its gravity, continue their slow journey across millennia, becoming part of new stories you'll never see. But you were there. You were witness to the hottest star you could imagine. You watched it live faster and louder than almost anything else in creation. You saw it tear itself apart in the name of creation. And now, all that's left, is stillness. This is the universe in its truest form. Not static. Not chaotic. But changing. Always changing. And maybe, just maybe, that's the message it leaves you with tonight. That everything burns in time. But what we burn for, what we give, what we shape, that's what lasts. So close your eyes now. Let your thoughts float free, like stardust in a nebula. Let your heartbeat slow to match the rhythm of distant galaxies. And as sleep begins to take you, remember. The hottest stars burn the shortest. But their stories echo forever.